When we talk about data structures, it's all about how you connect the pieces. Today, we're diving deep into one of the most fundamental of them all, the singly linked list. And more specifically, we're going to master how to add new links to this digital chain without, breaking the whole thing.
But seriously, think about that for a second. If you have a real-world chain, you can't just force a new link in. You have to be precise, you unhook, you insert, and you rehook everything carefully. That is the exact challenge we're going to solve today.
Okay, so before we start adding things, let's do a quick refresher on the layout. It all starts with the head pointer. This guy doesn't hold data, it just holds the address of the very first node. Each node itself has two parts, the data we care about, and a next pointer that, points to the next node in the line. And the very last node, its next pointer just points to null, which is our signal for the end of the line.
Here's our game plan. We'll hit insertion at the beginning, then at the very end, and finally, right smack in the middle. Then we'll do a quick recap to make sure it all sticks.
First up, inserting at the very beginning of the list. I like to call this one the headliner because our new node is about to become the new star of the show, the brand new head of the list. And trust me, this is the simplest and fastest way to do it.
The algorithm for this is super straightforward. First, you create your new node. Then, a quick check. Is the list totally empty? If so, great, this new node is the list. But if it's not empty, it's just two simple but crucial moves. First, you make the new node's next pointer aim at the current head. Then, you update the main head pointer to aim at your new node instead.
And this visual makes it crystal clear. Look at this. First, the new node's pointer connects to the old head. At this point, they're linked, but the list officially still starts at the old node. Then, for the second move, the main start or head pointer swings over to our new node. And just like that, we've got a new beginning. And this is what that magic looks like in code. That first line, new node.next equals head, is what keeps us from losing the entire rest of the list. You're hooking it up first. Then, the second line, head equals new node, makes it official. It declares the new node as the new starting point. Two simple lines, but believe me, the order is everything. Now, the real beauty of this method is its speed. It has a time complexity of O of 1. We call that constant time. So what does that mean? It means it doesn't matter if your list has 10 nodes or 10 million. Adding a new node to the front takes the exact same tiny amount of time. It's incredibly efficient.
All right, let's move on to our next scenario. We're inserting at the end. Now, unlike our last move, this one requires a bit of a journey. We have to blaze a trail, traveling all the way to the end of the list before we can add our new link. The algorithm kicks off the same way. You create a new node, and you handle the empty list case. But step 3 is the big difference. We have to traverse the list. That means we hop from node to node to node until we find the one whose next pointer is null. That's our target, the last node. Once we find it, we just switch its next pointer from null so it points to our new node.
So let's walk through this journey visually. We start by creating our new node, and notice its next pointer is already set to null because it's about to be the new end of the line. Now, to find the current end, we need a guide. So we create a temporary pointer, we'll call it PTR, and we place it right at the start of the list. And now the trip begins. We just keep asking PTR one question. Is the node you're pointing to null? Nope. Okay, move to the next one. How about now? Still no? Keep going. We just repeat this simple check until PTR lands on the very last node in our list. And here's the final move. Once our trusty pointer, PTR, has found that last node, we just update its next field. We tell it, hey, instead of pointing to null, you're now going to point to the address of our new node. The connection is made, and our list is officially one link longer. All right, now for the most delicate operation of all, inserting right into the middle. With this one, we're not just tacking something onto an end. We are carefully splicing a brand new link into an existing chain. And I'm telling you, the order of operations is absolutely critical if you don't want to break everything. So here's the game plan. We create our node, we travel down the list, but this time we stop at the node that's just before our insertion spot. Now listen up, because the order of steps 3 and 4 is non-negotiable. You absolutely must first connect the new node to the rest of the list. Then, and only then, can you go back and redirect the previous node's pointer to the new one. Okay, let's see this in action. It'll make more sense. Here's our list, and our goal is to get this new node to fit right in between the first and second nodes. This is the most important first move. We take the new node's next pointer and make it point to the second node. So, why do we do this first? Think about it. The only thing that knows where that second node lives is the first node's next pointer. If we broke that link before making this new one, the entire rest of the list would just be lost, floating in memory forever. So we secure the back half of the chain first.
Okay, now that the back half of our chain is safely anchored to our new node, now we can perform the second operation. We go back to that first node, we break its old connection to the second node, and we rewire it to point to our new node instead. And boom, the sequence is complete. The chain is fully intact and our new node is sitting perfectly integrated right where we wanted it to be.
So we've covered the headliner, the trailblazer, and the interloper. Let's put all three of these methods side by side so we can really see how their core logic stacks up.
This table really sums it all up. You can see the clear trade-offs. Inserting at the beginning, no traversal needed, so it's O of 1. It's basically instantaneous. But to get to the end or the middle, your key challenge is traversal. You have to walk the list to find your spot, which makes both of those operations O(n). That means their performance is tied directly to the size of the list. That's a critical distinction to remember.
So now you have the complete blueprint for adding links anywhere in the chain. It all comes down to being really careful with how you manage your pointers. But of course, this brings up the next big question, right? We're great at adding links, but what happens when you need to take one away? Well, we'll have to save that one for next time.